Welcome to Breadboarding. In the previous video we got the Intel clock controller set up and we've got the recording from the logic analyzer of the various signals here that we're going to try and reproduce using a programmable logic device. And in this video we're going to go through the configuration of the PLD and then testing it to see if we can replace the Intel clock controller and Intel bus controller. So this is part 6 of the Breadboarding Labs mini-series on programmable logic devices. And in the previous video we covered a lot of the background to the Breadboard 8088 PC, used the Intel 8088 in maximum mode, using a bus controller for a lot of control signals and the clock controller for all of the timing. And what we went through in some detail is that we're going to try and replace this with one ATF750C. To do that we need to divide our input clock frequency by 3 and give an output with a 33% high, 67% low duty cycle. We need to ensure we've got correct timing for reset, for ready and wait states, and in this video we're going to compare the original 8284 clock controller with our replacement, and we're also going to look at how to produce the various I/O signals as well. I'm just going to go through a few of the diagrams that we did in the previous video. If you haven't seen the previous video, there'll be a link for it at the top of the screen and also down in the description below. So this is the diagram in the data sheet for the clock controller, and all we were showing here that we're not going to try and reproduce the crystal oscillator input. We're going to take external input, so the external frequency input EFI here. We've got to do a divide by 3. We've got various flip-flops here, some with rising clocks, triggered on rising clocks. These two here are triggered on falling clocks, so we need to take into account that. And this circuit down here handles the wait states with the CPU ready. This provides the CPU clock signal. This is the CPU clock signal divided by 2 with a 50-50 duty cycle is the peripheral clock, and this output here is just the crystal oscillator buffered. And then we've also got up here the active high reset, which is used by the 8088 CPU itself. Now this was a divide by 3 circuit I came across from the URL down the bottom here. Now when I looked at this, you can see here this was the output I was originally using, but you'll notice that the duty cycle here is 67% high and 33% low, which is actually the wrong way around. We actually needed to take the 3367, so in fact I changed the design to use this output here, which effectively means we don't need to worry about that gate there and we just take the output from there. We also covered what the bus controller does, and basically the green signals here are available on the CPU when it's in minimum mode anyway. The orange signals here are different to the orange signals here, so we do need a circuit to reproduce these, and the grey ones are ones that we don't need to worry about. And this diagram came from one of the documents I referenced. The only thing we've got to be careful of is that the polarity of this memory I/O differs between different data sheets, so we do need to make sure that the 8088 side of things is the one that we use. I think the 8088 and 8086 had slight differences in this area. Now, produced in the new version, you'll see this is the Breadboard 8088 PC version 2 schematic that I've been working on, and what I did here is reproduce the various parts of the circuit diagram to make programming the PLD easy. And you'll notice here that I've got the Q10, Q11, these are the flip-flops references that I'll be using in the PLD design, and then the flip-flops here will just be the flip-flops associated with the output pin. And you'll notice here that the output of this gate is now not connected, and in fact we're taking this output here to feed into the various clock circuits. Down here at the bottom here we've got our control signals, so we're taking in the memory / I/O, just need to check the polarity there, our read and write enables, and we're outputting the I/O read, I/O write, memory read, memory write, which are the signals that the PC used. So what I need to do now is to look at programming the PLD. So this is the PLD design file. So I've already created a chip label for this. So the inputs, we've got the oscillator output. This initially will be 14.3 megahertz. We've got the read, write, memory I/O line. Now I do need to check the polarity of this on the real chips. Then we've got our ready active high and AEN active low. This one's going to be high when everything's okay, and will go to ground when it's needing to add wait states. This one will just float to high, so we don't need to tie it to anything. And then on the output, we've got our ready output. We have the clock 88, slight typo. We've got an inverted clock 88, which you may keep, we may not need it. I think this was mainly used for the DMA logic, so we might be able to get rid of that. We've got the memory read, memory write, IO read, IO write, peripheral clock. We've got the active high reset, which is what the processor uses, and then active low reset tends to be used by quite a number of other chips. And then this is the input for the power good sort of reset input. Now the key thing we're using here, as we covered in the previous video, we're going to be using some of the pin nodes. So in fact, if in the previous video we covered this, and in fact what we're going to be looking at doing is using the Q1 flip-flops here, so we can actually drive things into the Q1 independently from Q0, which will then also be going to the potentially the output pin. But we're going to be making use of the Q1 flip-flops in this particular case. And then the key thing here is that we've got our circuit, so this divide by 3 here produces our 3367 duty cycle. Did actually have to change this to be the correct polarity. So you'll see here that this was the original output using the OR, and this is now being changed just to have this output. So the key thing here is that we've actually got the ability to have different clocks. So you'll see that the clocks on some of these are CK falling, and the other ones are using the clock CK rising. So this is the thing we needed. And then these are the rules down here for the IO read, IO write, memory write. We just need to check the polarity of these signals here. So we just need to program the chip. So this is the 750C already in the programmer. So this is the T56 programmer. So this is a more expensive one. It's been replaced by I think the T76 now. They're about £340. So they're not cheap, but they're the only devices I've been able to find that will program these more sophisticated chips. So we're just going to read it first. Again, that's always worthwhile doing, because if you haven't put the chip in quite right, it will warn you. So that's read the chip, and then we're just going to load our GED file. So the version 2 GED file. We'll program this, and we will disable the lock bit so we can reread it if we want to. Okay, so that's programmed. So we're just now going to put it in the circuit. Just take it out of the programmer. Okay, so we've got the power in there. So we now just need to wire in a couple of signals. So we need to wire in the 14.3 megahertz output here, and wire that into the clock. So the clock is the top pin up there. Okay, so that's clock. We also need to wire in the res bar. So I'm just going to get a jumper lead and wire that in from the res down here. That means when the reset button or the power on reset comes on, that'll be okay. We also need to plug in the output from the signal generator from here. This needs to go to the ready input. I just need to wire in the additional logic analyzer signals. So clock 88 out of the 750 is purple. Clock 88 bar is blue. Green is reset active high. Yellow is reset active low. Ready for the 750 is orange. That is up there. Then peripheral clock for the 750 the clock, which is there. Okay, so that is wired up. At the moment it's still working off this 14.33 megahertz crystal, so I'm going to go back and rerun the logic analyzer. Okay, so I had to change one of the wires. I just missed where the hole for one of the clock pins feeding into the output of the oscillator. When the camera's overhead, you can't easily look at the board from overhead, and so sometimes you get the odd hole one out, so that's been fixed. I've also dragged the various pins so they're together, so you can see that we've got the reset from the original 8284 with the 750 reset. We've got the clock and the 750 clock, the ready, so they're all together so that when we run this, hopefully we'll be able to get a comparison fairly well. So what I'm going to do now is just to run this up, waiting for trigger, power it on. So if we zoom out, we can see that from the power on, we've got about 420 milliseconds for the power supervisor to give us our power good, or the /res goes high. So we can see that the reset for the 8284 goes from high to low to bring the processor out of reset, and similarly for the 750. So let's drill into this transition here and just have a look. Now generally the reset is supposed to be aligned with the falling clock signal. So we have the original 8284 here. Now you notice here that the duty cycle here is not really that close to 33. It's more like 40, 45 here. Can also be related to the glitch filter settings, in that because of the frequency we're running this at, then it does tend to pick up quite a lot of minor glitches. So by setting the glitch filter settings, if we have a look at them, you'll see that you have to tune these glitch filter settings when you're running at very high frequencies. But if we want to pick up the frequencies down here to be quite accurate, then you do need to run this at high frequencies. So what we can see here is the power good signal comes in here, and if we just put some of the timing markers in here, so we can see that the reset for the original one is aligned really to the falling edge of this clock here, and the reset on this one is I just put it there, it's very close, within probably 2 or 3 nanoseconds of the falling edge there. So the reset there is again aligned with this clock signal here. So I think the reset would appear to be on the falling edge of the clocks, which is what we wanted it to do. You'll notice that the duty cycle up here for our clock for the 750 is actually 33.33%. That's pretty good. The one up here isn't quite as good, and they're both actually slightly shifted. Now I was thinking about this, and I think probably the reason here is that the flip-flops which are used to determine the divide by 3, when it's powered on, these will be initialized at different points in time. So the 8284 will clear those at a different time from the 750. So I suspect the reason why these are shifted slightly is just because of the way how the registers for these are cleared. Now we don't really want to clear these on the reset, because if you press reset, then the CPU would never come out of reset if the clock was also reset as well. So this is probably just down to the power on activity. We don't actually need these clocks to be synchronized. All we need to have is that the outputs here are consistent with the ready signals and things as well. So the reset's okay. The clock is probably better from the PLD than it is from the 8284. It's certainly closer to the 3367 specification. Now if we have a little bit of a look out, if we look at down the bottom here, we can see that the peripheral clock then is about half the frequency, and this one is 47% duty cycle, whereas our 751 is almost bang on 50%, so that's good. Then we've also down the bottom, we've got our inverted clock as well, which was originally used in the DMA logic. I'm not sure if it's still used, so we might be able to get rid of that. And also the inverted reset is used by quite a few chips. The Intel processors require a positive reset, but a lot of other chips require a active low reset, so that's the reason why I got that one there. And then the only other thing we need to look at is the wait states. So if we have a look here, we can see that this is requesting a wait state, and here we've got a period of about 418 nanoseconds. Here it's sort of around about 180, 210. And if we go along, we'll see that because of the relative phases of these, that these will vary a little bit. And in general, if we look at this, so if we look at this particular one here, this is aligned to the falling edge of that one, and this is aligned to the falling edge of that one. But again, depending on the relative timing of the frequency generator that I get out of the logic analyzer, then you'll have different periods over here. And I think if we go along here, we may very well find, there we go, we've got another one here where we've actually got a longer period up there and the shorter period below. So again, this one is aligned with this falling clock, and this one here is aligned with this falling clock. So looks like the ready wait states appears to be working okay. So I think the logic analyzer output shows that we're certainly getting something out of the PLD which is comparable to the 8284. In some cases is actually more accurate, and I guess we'll just have to see when we plug this into a real 8088 processor to see whether the PLD version works as well as the 8284, but I think it's certainly good enough to give it a go. And the differences that we're really seeing here is probably more down to the difference in the power on reset state of the flip-flops which are used to do the divide by 3, and we could look at trying to do more there, but I don't really think it's necessary. The only outputs coming out of here really that need to be synchronized are the clock output and the ready output and the reset outputs, and those all seem to be aligning on the various falling edges of the clocks. So the reset is on the falling edge there, the ready signal is on the falling edge of the appropriate clock as well, and we also seem to have our peripheral clock seems to be okay, and so I think that's a pretty good result. So the rules to actually implement this we couldn't have done with the earlier PLDs. To do this we probably need 2 or 3 PLDs to do it because of the different clock requirements. So this really has made it much simpler to do in a single chip, although needing to have a more expensive programmer for it. So I think I've pretty much come to the end of what I can do with PLDs. So I wanted to get this sort of complex PLD working, and the fact that it is working well enough probably to be able to feed it into the next project. What I'm going to be doing over the coming weeks is finishing off the design for my version 2 breadboard PC, and this will be a simplified one that I talked about in the end of series video. So this will be removing direct memory access from the design, which will simplify things. It will also be running the CPU in minimum mode rather than maximum mode. We're going to eliminate the bus controller and the clock controller and replace it with this sort of chip that we've got at the top of the board here. And I'm also going to improve the layout of the board, make it a bit neater and tidier, and I'm going to be using some bus rails on Breadboard strip board to actually act as the system bus, which should hopefully be a bit more reliable and won't have the leads pulling out quite as easily as you otherwise would have had. So if you don't want to miss out on the future videos, please hit subscribe and you'll get to see the Breadboard PC version 2 when it arrives. If you found the content interesting, please hit like. It just helps to make the videos available to more people on YouTube. Thanks for watching.